Hello, and thank you for coming to view my talk today. I'm excited to present our new tool, the Terrestrial Exoplanet Simulator, TESS. I'm Pete Bartram, and this work was performed with Alex Wittig, who is also from the University of Southampton. I'm going to talk about three things today. Firstly, I'll explain what TESS is, and I will do my best to convince you that it is a good tool for use with problems in astrodynamics. I'll then go on to explain a bit about our model and its numerical features. And finally, I will show results from a range of numerical experiments, including the 2029 Apophis flyby. Okay, so what is TESS? TESS is an open source C++ package that we have developed for modeling exoplanet evolution over billion-year timescales. We've used this tool previously to study celestial mechanics, specifically the dynamics of solar systems during periods of instability, where we have integrated precisely all the way to collision of planets. TESS is available from my GitHub at this link here, and you can also find this on the final slide of the talk. We offer an implementation in purely double precision floating point for portability, but also offer an extended precision version where that is used exclusively in the Kepler solver, which improves the overall precision of the scheme as well. Presently, TESS only contains gravitational interactions, but it can easily be extended to include arbitrary perturbations as well. So why astrodynamics? So I'll start this section by saying that we're only looking to address numerical integration error here and not modeling error. Okay, so that said, mega constellations are rapidly changing the low Earth orbit environment, and an object in Leo will perform, on average, roughly 150,000 orbits over a 25-year lifetime. And over this timescale, we find that the energy conservation in TESS is precise to machine precision. So that means that there's only an error in energy of 1 part in 10 to the 15. The TESS model takes advantage of the dominant known Keplerian motion and is therefore faster than a general purpose ODE integrator. And as we will see, the masses present in astrodynamics, as opposed to celestial mechanics, are highly favorable to the efficiency. So that's the motivation covered, and now I'll go on to explain a bit about how our model works. We have chosen to base our scheme on the classic Onca method, and for this we also chose to use a coordinate system that is common in celestial mechanics, the so-called democratic heliocentric coordinates. These coordinates describe position relative to the central body and momentum relative to the barycenter. And using these coordinates allows us to derive an n-body perturbation method using conjugate position and momenta. The Onca method can be seen in this diagram here, where the Keplerian reference orbits are shown as a dashed black line. The true orbits, so those including the perturbations to the Keplerian reference orbits, are shown in red. We use Q to represent position and P to represent momentum, and therefore the reference trajectory state vector is given by Z, and the state vector for the true trajectories is given by z hat. So therefore, our Onca method is given by z hat equals z plus dz. And this means that the perturbation terms, which I will refer to as the deltas throughout, are dz. So if we look at the diagram again, and specifically at the initial positions in green, at this point the size of the deltas, so the deviations between the true trajectory and the Keplerian reference trajectory, is small, but over time these deltas grow larger. And when the deltas grow too large, it's necessary to calculate a new reference trajectory through a process called rectification. And to do this, we simply add the reference trajectory together with the deltas and use these as a new reference trajectory, z prime. And at this point we also set the deltas equal to 0. So typical sizes for the deltas relative to the reference orbits are 10 to the minus 2 for the outer solar system and 10 to the minus 4 for the inner solar system. And by keeping the delta terms small, the Onca method reduces the truncation error in the integration of the deltas and therefore reduces the computational requirements on the integrator. So finally, we can write the equations of motion for the deltas themselves as dz dot. So in democratic heliocentric coordinates, the Onca method equations of motion are given by these expressions here for the change in position and momentum of each body. As we're working in democratic heliocentric coordinates, we need to specify an index for the central body, and as is conventional, we opt to use 0. So if we look at dp dot first, and specifically in this trailing term, we can see that the summation index begins at 1, and this means that this term only describes interactions between secondary bodies. The deviation of a particle from the two-body reference orbit over time is instead captured by this leading term. And so long as dq is small in this term, then the contribution to the acceleration also remains small. And it's this subtraction here that enables the Onca method to become so efficient. So if we now look at dq dot, which is the velocity, we can see that the velocity depends on this momentum over mass, as we would expect, but also with this additional term present. So to understand this term, let's consider just a two-body case after a rectification, so in other words, with the delta set to 0. In this case, all we're left with is one term, which turns out to be the negative momentum of the central body, p star. So therefore, we can see that in the absence of strong perturbations, as is expected for the most part of integrations, the growth rate of the deltas depend upon the momentum of the star. Maintaining the deltas at a low level is key to maximizing the efficiency of any Onca method, and therefore the efficiency of TESS depends upon the motion of the star. And finally, the motion of the star depends upon the ratio of the mass of the primary to the mass of all secondary bodies. And we'll see later how this ratio affects the performance of TESS. Now if we go back to the original equations, we can see that the cancellation that gives us our performance is also a source of numerical error, owing to the subtraction of two like terms. So in order to ensure that we do not lose significance due to this term, we use a known mathematically identical formulation of the differential force that's more numerically robust. And these become our final equations of motion. The relatively small size of the deltas to the reference trajectories means that the dominant source of error growth actually becomes the calculation of the reference trajectories themselves rather than the integrator. And in our case, this means we need to calculate them to machine precision. We use a stimp function-based universal variable solver along with the f and g functions to propagate our reference trajectories. And we opt to use the method outlined in the WH-FAST algorithm of Hanno Rein and Dan Tamayo, with some extra additional modifications such as compensated summation to improve the precision in our use case. We offer two implementations of TESS. One is in purely double precision floating point, and there is an additional one where the Kepler solver is allowed to use extended precision floating point. In other words, the force model and integrator are all still in double precision. Results from both of these implementations are presented later. To integrate the perturbations, we choose to use an Everhart-Radau scheme, and we base our implementation on that of Hanno Rein and David Spiegel in AAS 15. So that is the description of our model, and I will now move on to look at numerical results of experiments performed with it. We use compensated summation in multiple places throughout TESS. We use it in the Kepler solver, we use it in the integrator, and we also use it when we rectify. So therefore, to highlight the benefits of using compensated summation, we've performed a series of integrations with compensated summation disabled in each of those previous locations to see what effect this has on energy conservation. For this, we perform integrations of the inner solar system over 10 to the 8 Mercury orbits, and each of the lines plotted are the RMS values of 20 realizations. As a baseline for comparison, the red line represents what we're calling a naive Onca method, so this is with all of the compensation features disabled. We can see that this is one of two configurations with the worst performance. And in contrast to that, TESS with default settings, so with all compensation features enabled, shown in orange, is 2 orders of magnitude better in energy conservation than the naive Onca. We can see that disabling an individual compensation scheme can cause a degradation in performance of between 1 and 2 orders of magnitude compared to TESS with default settings. And not compensating the reference trajectory calculation in the F and G functions is akin to not compensating throughout. And finally, if extended precision is permitted for use exclusively in the Kepler solver, then it's possible to improve the energy conservation by another order of magnitude, and at the same time ensure that no energy error is visible in over the average lifetime of an object in LEO, which is the first thing that we think that makes TESS a great tool for use in astrodynamics problems. The efficiency of TESS depends upon keeping the deltas as small as possible through the process of rectification, which resets them to zero and allows them to grow slowly from there. As I showed earlier, for the two-body case, the rate at which this happens is related to the momentum of the central body and therefore to the mass ratio of the primary to the secondary. And we therefore expect to see an efficiency profile that depends upon this ratio. To test this, we performed integrations of 21 circular two-body systems over a period of 10,000 orbits with a primary to secondary mass ratio that ranges from that of the Sun and Jupiter to that of the Sun and Mercury. In the left-hand panel, we see that the relative energy error for TESS and IAS-15 is identical, and it also shows no mass dependency, as we would expect. Looking at the right-hand panel, we can see the runtime of the same set of experiments, and we can see that IAS-15 in green shows no runtime mass dependency, whereas the Onca-based schemes do. In the Mercury mass region, TESS is roughly 40% faster than IAS-15, but this performance boost falls to only 5% when looking at Jupiter mass secondaries. Applications in astrodynamics typically have a mass ratio smaller than that of Mercury to the Sun, which means that the efficiency gains are the second reason that we think that astrodynamics problems are a great application domain for TESS. So far, we've just looked at the performance of TESS when bodies are well separated and the perturbations are therefore small. So we now turn to look to see how TESS performs in the presence of close encounters. We choose to look at a simplified model of the Apophis flyby in 2029 used by Davide Amato, and we propagate only the Sun, Earth and Apophis and only consider gravitational interactions. We model from 1979 to 2079 with initial and final conditions generated using a quadruple precision integrator and the state vector at the predicted point of closest approach in 2029. If we look at the left-hand panel, we can see the trajectory followed by Apophis and its transition from the Apollo to the Athens asteroid groups in 2029. And if we look at the right-hand panel, which shows the separation between Earth and Apophis, we can see that there was a close approach, almost within an Earth Hill radius at 10 to the minus 2 AU in the early 2000s, but that the closest approach is yet to come in 2029, and in 2029 it will pass closer to Earth than the Moon. We're going to look at the total energy and positional error of Apophis at the end of the simulation in 2079, and also at the positional error at the time of closest approach in 2029. For this, we performed 60 integrations of identical initial conditions for each scheme, and we varied the tolerances across a wide range to produce convergence diagrams. First, let's consider the performance in 2079. The energy error is shown in the left-hand plot, and the position error of Apophis is shown in the right-hand plot, and these are both plotted against runtime. In the truncation-dominated region, the Onca-based methods are faster than a general-purpose integrator. However, once the round-off error region is reached, all schemes, with the exception of the naive Onca method, converge to roughly the same value at 10 to the minus 15. Each scheme has a recommended operating tolerance, and the furthest right data point for each scheme represents the results of an integration with this default tolerance. So using this data point, we can see that TESS is the fastest scheme, even in the presence of close encounters. In the right-hand panel, showing the position error of Apophis, we find that IAS-15 converges in a similar fashion to that seen in the energy plot. Whereas for the Onca schemes, the positional error is either excellent or very poor with no transition region. What's important is that the default tolerances for TESS are well within the region of good performance. Finally, we look at the error in position of Apophis on the B-plane at the point of closest approach in 2029 for a given runtime. Looking top down on the orbital plane of the Earth here, and Apophis here, both moving as such, then at the point of closest approach, the B-plane is the plane intersecting the two bodies that is orthogonal to both the orbital plane and the velocity. Farnokia found that in order for Apophis to be placed upon a resonant return trajectory, and therefore risk impact with the Earth, it must pass through specific circular regions of space on the B-plane at the point of closest approach. And these regions on the plane are known as keyholes. The size of keyholes in this case range from 6 centimeters to 600 meters, which corresponds to this region here, with the majority of keyholes being of the size that is found in this region here. So we can see that the precision of TESS in position error on the B-plane is now suitable for modeling near-Earth object dynamics, whereas the naive Anker method is not capable of achieving the precision to say whether a keyhole was passed through or not. And that's our third and final reason that we feel TESS will be very useful for the study of problems in astrodynamics. So just to summarize briefly, so the three reasons that we think that TESS is great for astrodynamics. One, it achieves machine precision integration over the average lifetime of an object in LEO. Problems in this field fall in the most efficient mass ratio region. And finally, the position error is precise enough to model NEO dynamics. So that is it from me. Thank you for listening to my talk, and I will be at the Q&A session on Wednesday, February the 2nd at 9:30, and I hope to see you there.